Hi everyone, this is Bokun Wang. I'm a visiting student in Professor Rich Tarrick's group, and today I would like to present our paper IntSGD written by Konstantin, Dmitry, Peter, and me. The problem we aim to solve is to minimize this function, which is in the finite sum form, and each of the local loss function is accessed by the stochastic oracles. So we want to solve that problem by distributed SGD. And we can do compression on the local stochastic gradients to further reduce the communication cost. So a natural question is how to choose the compressors. Here are the compressors, including the unbiased ones and the biased ones. And are there any limitations of those existing compressors in practice? The first issue is that it may take more time with GPU memory. Like in Dithering, we need to do elaborate decompression, and in SunHD, we need to implement the new primitives based on the bit level operations. And the second issue is that current deep learning frameworks predominantly rely on the reduce. However, many popular compression doesn't support reduce, like the SunHD. Here's an example. So gather we aggregates the result on the master by first collecting all of them. However, the aggregation can be computed on the fly by reduce, which is more efficient. And SunHD, if we implement it by reduce, it may lead to wrong results. And some compressors need double compression. Like in the natural compression, if we aggregate this to quantize the values, it will lead to a result that need to be quantized again into 1 or 1/2. And the last issue is that sometimes the master could be computationally weak, like it's a network switch and can only do integer addition. Then most compressors are not applicable. On the contrary, integer compression has this merits, like it doesn't need double compression, decompression, or extra sequences. And it's also support or reduce and supports network switch as the master. And it can also work with existing primitives data types like integer 32 or integer 8. This idea is very simple. However, simply applying the integer compression in distributed SGD will lead to a poor performance because the values of those gradients are all close to 0. So if we apply the integer compression, we basically compress almost rounding every value into 0, and it will lead to a bad precision. So the idea is to scale it before compression. So we scale it before we do the integer compression, and then we can aggregate that quantized value, and the rescaling part can be done locally after the aggregation. So we first, on each local worker, we first compute the stochastic gradient and compress it by scaling and rounding. And then the master can aggregate those values and broadcast it back to the devices. And then we can do rescaling and do the gradient step. So the key challenge is that how to choose the value of scaling factor. We can tune by grid research or use the heuristic method proposed in this paper, but both of them are very expensive and no convergence series provided. And to solve this, we propose the adaptive scaling factor, which is cheap to compute and also lead to sharp convergence rate. It matches the convergence rate of full precision HGD up to a constant factor in the convex, non-smooth case, convex and smooth case, and non-convex and smooth case. Here are some experimental results. So it outperforms HGD and natural HGD in terms of the total transmitted data. It can also match the heuristic-based profiling approach proposed in this paper. However, our method is very cheap, but the profiling or grid search method proposed in previous paper is very expensive. So thanks for listening.